In this video, we're going to be talking about r squared and some of the interpretation for r squared and some of the limitations for r squared. All right, so let's assume that we have the simple linear regression model yi equals beta naught plus beta 1 x sub I plus epsilon sub I, okay, for I equals 1 to n. All right. And in real life, we do not know what this model is exactly, right? So we don't know exactly what is beta naught, the intercept, and what is beta 1. We also don't know exactly what the model errors are, epsilons, right? So what we do is we collect data, and then we estimate all these guys. Okay, but for the purpose of this conversation, it's going to be helpful if we go ahead and let's assume that we do know what these guys are, and let's calculate y 100% based off of an assumed exact model. Okay, so this is purely for the purpose of this conversation. Let's go ahead and define beta naught, the intercept, to be equal to 1, and beta 1, the slope, to be equal to 2. Okay. Also, I have some epsilon values I'm just going to go ahead and use, so let me paste them in. These are some just random numbers for the model error, right? And of course, the sum of these should be equal to 0. All right, and xi, let's go ahead and use just the numbers 1 to 10. All right, so let me go ahead and click these and drag it down. All right, yi, let's assume y is completely determined by this model. So I'm going to use the formula equals, and I'm going to use the cell reference plus the slope times x plus epsilon. All right, so I'm using a formula to calculate this, and I'm going to need that formula for all the different x values. So let's go ahead and lock in where the intercept is. Use dollar signs to lock that number there, or that cell reference there. And the same thing for the intercept, or for the slope. Okay, press enter. Click on that cell, and if you get your cursor to look like a little cross, click and drag. And now calculate all of my y values based off of that cell reference. So we should have the intercept plus the slope times x plus epsilon, which is this model over here. Okay, press enter. All right, so now let's go ahead and assume that this is my data. So let's highlight that. That's data. All right, and now if I want to figure out what r squared is, I could use the data analysis tool pack in Excel. So let's go ahead and do that. I'll go to the home, click data, and then data analysis. All right, press regression. Okay. All right, the y values, let's go ahead and click and drag and hold. The x values, get your cursor in there, click, drag and hold. Okay, so there's my x and my y values. And then labels, always click that. That means that you've highlighted your labels when you highlighted this data, which you should always. The output range, I like to go ahead and just put this output, put my cursor in here, and let's go ahead and put the output in that cell. Okay, and it'll use all these cells below it. I want to include the line fit plot, so click that, and then press OK. All right, so let's look at this line fit plot. We see these little blue dots are x and y. These are our observed values of x and y. And the predicted y, we see it's doing a pretty good job. This is a good fit model, right? And here's our r squared value. Let me highlight it. A lot of times when I'm interpreting r squared, I like to go ahead and convert it to a percentage. So click that percentage and then have some more decimals. You can click this little over here. So format it, and I can say, okay, looks like 88.47% of the variability in y is explained by the model or by the regression. In this case, since there's only one x variable, it's explained by that x variable. So that's a pretty good percentage. And we expected that because of the way we constructed our data, right? And we can look at the estimates of the intercepts and the slope. And of course, these are estimates. We have a small sample size, so they're not going to be exactly equal to what we know that they actually are. But Excel gives us all this other information. It also gives us the residuals. And it gives us lots of information, but basically right now I'm focusing on what is R squared. All right, and R squared is telling me something about the fit. It's telling me that this is a pretty good fit. Okay. All right, and so what would a bad fit look like? Okay, so let me highlight this data and copy it and put it in the next sheet. Let me paste it here. I'm just going to go ahead and paste it regular. Okay, and so how can I make R squared be approximately equal to 0? Well, if R squared is approximately equal to 0, that means the regression, it doesn't do a good job of explaining the variability in Y, right? And right now, the way I've written it right now, I have yi equals 1 plus 2 times xi plus epsilon sub I, right? And so we saw using this model in the previous spreadsheet that I just was looking at, that this R squared, it was very high, and it did a good job of estimating, the variability in Y was well explained by this model, right? Okay, so if the variability in Y is not explained by the model, or R squared is approximately equal to 0, basically this term here needs to go away, right? We need to see that yi has nothing to do with x, right? The model does a poor job of explaining the variability in y. So to do that, let me change beta 1 equal to 0. Let's make my slope equal to 0. Okay, let me highlight that change. Okay, and then let me go ahead and run the regression again and see what R squared is. Let me go to data analysis, regression, all this stuff. It's going to stay the same because all this stuff is in the same location. Press OK. Okay, and what do we see? Okay, so we've changed the way the y's are being calculated, right? Because now beta 1 it's basically just this random epsilon plus 1, right? So we see the random variability, and this predicted line it's not doing a good job, it looks like, of predicting what the values of y are, and we do see that very low R squared. So let me highlight that, maybe make it a percentage and move it over. So we see 8.91% of the variability in y is explained by this model, right? Which is very, very low. All right. The theoretical real value of R squared is actually 0 based off of the way we constructed our or calculated our y values. It had nothing to do with x. R squared is actually 0, but of course, this is an estimate of R squared, right? Based off of assuming that this is just data, okay? So we're seeing that very low R squared value, that the variability in y is not only 8.9% of the variability in y is explained by x, according to this estimate. Okay, so then let me go back here. I'm going to copy this again. What about R squared being approximately 1? How would that look different? Okay, let me paste this. What would need to change to make R squared approximately equal to 1? If R squared is approximately 1, then my model error needs to be 0, basically, or approximately 0 for all my observations. So that's let's see what happens here. Let's go to data analysis, regression, okay? And all this stays the same. Press OK. All right. So we see the predicted value and the actual y value there. The observed y value and the predicted y value are lining up on each other. Okay, so this is a perfect fitted model, and we see that r squared is exactly 1, actually. Okay, so if epsilon is really small, so the model error is 0, then it's going to be exactly 1. If it's really, really small, really close to 0, then it'll be approximately 1. Okay. All right, let me go back to the original, copy it again. All right, what about overfitting? What changes when we overfit? Let me paste the data in. R squared when we overfit the data. Okay, so let me insert. I'm going to insert here, and I'm going to insert an x squared term. Okay, and I want this equal to x squared, right? So use that formula, drag it down. Okay, so you see it's just taking the x value and it's squaring it. All right, so I didn't change the way y is being calculated. So if I include x squared, right, so y, it's still following this model. Let me go ahead and draw this. yi is still following this model, 1 plus 2 times x sub I plus epsilon sub I, right? But I could say I don't know that this is the right model, right? I don't know that that's the right model. I could run my regression model as yi equals some intercept term plus a linear term plus a quadratic term, right? And of course, since I know this is the right model, I know that this is actually, overfitting, right? I shouldn't necessarily do this, right? But in reality, you don't usually know your real model, so you might try doing this. And how, if you were to do this, how would that affect your r squared? Let's see. So let's go to data, data analysis, press regression. Okay, your y values, it's still going to be right there. But your x values now, let's delete this. And let's highlight both of these x values. Okay, so I've highlighted all of them. So B and C. Okay, I still have the labels, and I still want my output on the same page. So I'm going to press OK. Okay, I should have 2 plots, one for x and one for x squared. Okay, so, and let's see, what is our r squared value? Home. Okay, let me go ahead and change that to a percentage and have more decimals. Okay, look at that. It went up. It's 90%. So 90.78% of the variability in y is now being explained by our model. It looks like we just created a better model, right? If you believe that r squared picks out the best model. Okay, and this is a point of caution because it doesn't. R squared does not pick the better model. We know that this model is correct, right? And when we have the correct model being used, our r squared is only 88.47%. Okay, so r squared, it will increase just because you have an additional regressor. That doesn't mean that it's the best fit model, right? We know that because of the way we constructed what y is, we know this is the correct model. All right, so this 90% of the variability in y, it's very tempting to say this is the better model, but that's just a property of the way r squared is calculated. All right, so don't be tempted to make that that incorrect conclusion. Okay, so let's go over. All right, increasing the slope. Okay, so let me go back. All right, and let me highlight this, copy it, and put it over here for increasing the slope. Paste. Okay, so my model is yi equals, currently it's 1 plus 2 times x sub I plus epsilon sub I. Okay, and so what we want to talk about right now is what happens when I increase this slope. Say instead of 2, say I increase it to 4. Okay, so my model fit, I don't want to change the way the model is fitting. All right, I'm still going to use this exact same model, the same epsilons. I'm just going to change beta 1 to 4. Okay, and so you can see all my y values changed, right? So I've increased this, and so these guys, since they're all calculations, they're formulas, depending on these values here, they all changed. Okay, so let's see what happens. Let's go to data analysis, regression. Okay, I think I need to change this guy to being just the x values again. All right, labels, all that stuff. Okay, press OK. All right. So my line fit plot looks very similar. The slope is now much steeper, right? So slope used to only be 2, but now it's 4, so we do have a steeper slope. And this r squared value, let me go home, highlight it, convert it to a percentage. I just like looking at it as a percentage. Wow, that was a big increase. It's now 96%. But does this model fit the data any better? Of course not, right? This model, it has the exact same model error, right? The same model error. So this isn't a better fitted model than the one that we ran the first time, right? Same model error. Okay. It's not a better fit model. It just has a steeper slope. Okay, so you have to be careful about this. The steeper the slope, your r squared can artificially get larger. Okay. All right, the last limitation I want to talk about, r squared. Let me go ahead and highlight my data one more time and copy it one more time. Let me copy and then paste onto the last sheet here. Paste. Okay. Is increasing the spread. What happens to r squared when you increase the spread? So what I mean by that is, instead of x being from 1 to 10, let's make it from 2 to 20. I'm going to do even numbers, okay? I think if I do a few even numbers and highlight it, Excel gets the pattern and I can fill it all in. Okay, y was automatically updated. So I haven't done anything to my model. My model is still yi equals 1 plus 2 xi plus epsilon sub I. Also, I have not changed the number of observations I have. I still have 10 observations. The only thing I've done is I've increased the spread of x, right? X used to go from 1 to 10, now it goes from 2 to 20. Okay, so let's go to data analysis. I think that all this should stay the same. Okay, it does. All right, so now let's go look and see what our r squared value is. We have here it is. Let's press home, highlight, change it to a percentage. Okay, and we're seeing a very high r squared value, right? And the slope, it's the same slope, but it's over an increased spread of x, of the values of x, right? But the model error is still exactly the same. So this model doesn't fit. It's not a better fit, right? And yet it has a much higher r squared than when we only went from 0 to 10, when our data only went from 0 to 10. Okay, and that's another limitation of r squared, that when you have a larger spread of your x values, you're going to see a potential artificial increase in your r squared, and that's not necessarily due to that the model is doing a better job or it has a better fit of the data.